right, this video is an investigation on solving radical equations. So first of all, let's talk about the definition of what a radical equation is. A radical equation is an equation, so it has to have an equal sign, and it has a variable that you're solving for, like an x, underneath the radical sign. So let's look at which of the following of these things are radical equations. In this first equation, there's an x underneath the square root sign, so that is a radical equation. In the second equation, there's a radical, but the only thing underneath is a 2, so that's not a radical equation. This is just a standard linear equation because the x's are just plain old x's. In the third equation there's an x that's inside the radical and one that's outside, but this x that's inside the radical is enough to make it a radical equation. There's a couple ways we can solve radical equations. First, let's try to solve this by graphing. Whenever we want to solve an equation by graphing, what we want to do is we want to graph one side. So if we graph the left, we're graphing y equals 2 times the square root of x plus 1, and then a plus 4 on the outside. So that's just the square root shape. Move 1 to the left, up 4, and then stretch times 2 vertically. Next, we want to graph the other side of the equation, which would just be y equals 8. Y equals 8 is just going to be a horizontal line at 8. So the question is, at what x values do they intersect? And where they intersect is right here at x equals 3. We don't really care about the y value of intersection because in our original practice problem right here, there were no y's, there was only x. So we're looking for x equals 3. So the next question is, would you have gotten the same answer if you had graphed y equals x plus 1, the square root of x plus 1, and y equals 2? And the answer to that is yes, you would. So I've graphed those, and you can see they still cross at x equals 3, but the y value is now different. Again, the y value didn't matter, so that's the same solution. Why did we ask this question? We asked this question because in our original equation up here, if we had subtracted 4 from both sides to move the 4 over, and then divided both sides by 2 to move the 2 over, you would have had the square root of x plus 1 is equal to 2. And that's the equation we solved in purple. All right, let's look at solving equations algebraically. So your friend Ian Inverse is solving some math problems. So what is he going to do? If you're solving 2x equals 16, what is Ian Inverse going to do to get x by itself? Well, he needs to divide both sides by 2 to get x alone. If you're solving x divided by 3 equals 3, what are you going to have to do to get the x by itself? You're going to have to multiply both sides by 3. So we do that because multiplication and division are inverse operations. Now let's look at what happens with squares and square roots. When solving x squared equals 4, you're going to have to do what to both sides? You square root both sides. The next one, if you're solving the square root of x equals 3, then you're going to have to square both sides. We know that the square root of x squared is equal to x, and that if we take the square root of x and square it, that's also equal to x. So because of that, squaring and square rooting must be inverses or inverse operations. So if you had to solve the basic equation of the square root of x equals 3, you would need to do the opposite of square rooting. That means, what do you need to do to both sides? You need to square both sides. So if I square both sides, the square and the square root are opposites and undo each other, so just x is left on the left. And then I have 3 squared on the right. Well, 3 squared is equal to 9. So I get x equals 9. We want to check our answer by plugging back into the original equation. So if I do the square root of 9, is that equal to 3? Yes, it is. I always have to make sure with radical equations that I check my answers because there is no property of like a property of addition or subtraction for solving equations that says you're allowed to square both sides. It's a method we use, but it's not a property. So we have to check for extraneous answers. So here's an example to sort of show that. If I have x equals 1 and I square both sides, I get x squared equals 1 squared. So now when I square root both sides, I get the square root of x squared equals the square root of 1. Well, also, whenever I square root both sides, I always need to put a plus or minus with it. So that means I could possibly have two answers, because if I have x squared equals 1, then x could equal positive or negative 1. So just like with absolute value equations, when you solve square root equations, you have to check your answers, because sometimes you pick up an additional answer. So here's another quadratic. 2x squared minus 1 equals 11. And we're supposed to help Rachel radical solve this one. So the first thing I want to do is to isolate the term with the exponent. So to do that, I'm going to start out by adding 1 to both sides. On the right, that would give me 2x squared equals 12. Now I have to get rid of the 2 to get the squared by itself. So if I divide both sides of the equation by 2, I wind up with x squared equals 6. Now I have to undo squaring. The opposite of squaring is square rooting. And remember, whenever you square root both sides, you have to put a plus or minus in front, because I could have been either one. And I simplify. It's just x is plus or minus the square root of 6. If I were to check if both of those answers worked, does 2 times the square root of 6 squared, which would be 6, minus 1 equal 11? Yes, it does. And does 2 times the square root of, or negative the square root of 6 squared, minus 1 equals 11? Yes, that also works. So both of these solutions work, and a quadratic typically has 2 solutions. In example 5 here, we're trying to solve a radical equation. So again, we need to get the square root by itself. How do we get the square root by itself? We would add 1 to both sides. Then, just like before, we would have to divide both sides by 2 to get the square root by itself. Next, we have to undo the square root. So the opposite of square rooting is squaring. So now I'm going to square both sides. Then I just simplify. 6 squared is 36. I have to check and make sure this works. Is 2 times the square root of 36 minus 1 equal to 11? Well, the square root of 36 is 6. 2 times 6 is 12. And 12 minus 1 is 11. So check, that works, and our equation is solved. Notice we use the same method in both of those problems to solve. We isolated the square term in number 4 just the same way as we isolated the square root term in number 5. Just realize that just like sometimes the squared term might be something like an x minus 1 squared or 3x plus 4 squared, sometimes the radical will not just be the single radical of x. It will be something like the square root of x minus 1 or the square root of 3x plus 4. Either way, we're isolating the whole radical. So now we're going to try some that are a little more difficult. This is a radical equation. Here's our radical right here. So the first thing we want to do is to isolate the square root or the radical. In order to do that, we want to first move anything that's added or subtracted to the radical. So first I'm going to subtract 4 from both sides to get that radical by itself. When I subtract 4, I'll be combining like terms, and 2 minus 4 is negative 2. Next, I have to get rid of the 2 that's multiplied by the radical. To undo multiplication, I want to do division. Remember, when you divide the side by 2, it distributes to every term. So that would give me x minus 1 on the right. Next, to undo the square root, I'm going to square both sides. Now, when I square the quantity, I'm squaring the whole side. So when I do that, I have x minus 1 squared, which is x minus 1 times x minus 1. In order to do this multiplication, you either have to FOIL or use the area model so that you make sure you get your middle term right here of negative 2x. You cannot simply distribute the squared sign across the subtraction. This equation we have right now is a quadratic because it has a squared in it. To solve a quadratic, I start by getting it equal to 0. So I'm going to subtract the x and subtract the 1 to move them over. So I wind up with x squared minus 3x on the right. This again is still a quadratic, but it has a GCF of x. So if I factor an x out in front, my second factor will be x minus 3. Finally, I set each factor equal to 0. So x equals 0 will just give me 0, and x minus 3 equals 0 will give me x equals 3. So I have 3 and 0, which are two solutions, but I still have to check them to make sure they work in the original equation. To check the answer algebraically, I have to make sure I plug 0 and 3 into the original problem and identify if my solutions work. So let's start with that. My original equation was 2 times the square root of x plus 1, so I replaced that x with 0, plus 4 equals 2x, so again I replaced that x with a 0 also, plus 2. So does this work? If I simplify this equation, I get 6 equals 2. Well, that's not true. So x equals 0 is not a solution. I want to make sure I either cross that out or write extraneous next to it so I know that that answer doesn't count. Next, I want to check if x equals 3 worked. So I'm going to plug 3 in for both of the x's in the original problem. If I simplify that, I get 8 equals 8. So x equals 3 is a solution, and I'd want to circle that and include it as part of my answer. The other method I can use for checking is to check graphically. To check graphically, I want to graph the left and right sides of my equations. So the left side was 2 square root of x plus 1 plus 4, which was the half a sideways parabola moved 1 to the left and up 4, stretched times 2 vertically. And the right side of my equation is 2x plus 2, which is a line with a y-intercept of 2 and a slope of 2. So when I graph those two equations, I see they only cross one time. Where they cross has an x value of 3, and x was my original value in the problem, my variable, so x equals 3 is my only solution. For example 7, I'd like you to pause the video while you try this one, and then when you think you've got it, after you've checked your answer, you can see how you did. Okay, so in this one, we isolate the radical, so we would add 3 to both sides. Then we would divide both sides by 2 to get the radical all the way by itself. Square both sides. Remember, when you square the right, you have to square this whole thing, okay? Not just distribute the squared, so you should wind up with this middle term. Now, we didn't like that this was over 4 because I'm not a big fan of fractions, so I multiplied everything through by 4 to get rid of the fraction. That makes it easier for me to work with. So I distribute the 4 to everybody. That's a quadratic. So I set it equal to 0. And then to solve that quadratic, you can either factor it to get x plus 2x minus 2, or you can move the 4 over and square root both sides, which would give you plus or minus 2 as well. When we check our answers for this one, I plug in -2, and that gives me -3 equals -3. I plug in +2, and that gives me 1 equals 1. So both of these solutions work. And sometimes we have two solutions to a radical equation like this. Sometimes we have one solution, sometimes we have no solution. You just have to check. Sometimes when you have a radical equation, it's actually easier when there are two radicals in the problem. When we go to isolate the radical, there was already both radicals by itself. So now to undo the square rooting, we're going to square both sides. When we square both sides, the radical reduces out on both. So I'm left with something that's actually a simple linear equation. So I'm going to move the 2x over, move the 4 over. And when I get x by itself, I get x equals 7/2. I still do have to check to make sure that it works. If I plug 7/2 in for x on the left and 7/2 in for x on the right, do those two values equal each other? Yes, they do. So I know that x equals 7/2 is my solution to this equation. In that last problem, the two radicals made it easier. But sometimes when two radicals are in the same problem, or three radicals, it makes it more difficult. To solve this one algebraically is a nightmare, because when we square both sides, we're going to have to square this expression with two radicals. It's not so nice. So we could also do this graphically by just using our calculator, or since we're at home, I'm going to use Desmos. So I need y equals the square root of x plus 9. To get that, I can either type SQRT and it'll pop up a square root, or I could have gone to the little keyboard down here at the bottom and just hit the square root button and it would pop up a square root also. I need to be sure when I type my x plus 9 that that whole thing stays underneath. Then, if I hit enter, it'll go to a second equation. And my second equation is the square root of x plus the square root of 3. You can see Desmos automatically puts a little point right here where they cross, and the x value of that point is equal to 3. Again, I don't care about the y value. The x value is equal to 3, so that's the solution. If you needed to show your work for a problem like this, you could make a simple sketch of what were on your calculator, and that would be fine. All right, what happens if we have higher powers than just square root? So if we have a square root, we do the opposite by squaring. If we have a cube root, the inverse would be cubing. A fourth root, the inverse would be the fourth power, and so on. So whatever your index is of your radical, you're just going to undo that by raising both sides to that same power. So let's look at these for 10, 11, and 12. If I wanted to undo the square root of x equals 3, I would square both sides, and that gives me x equals 9. If I had the cubed root of x equals 3, I would cube both sides, and that would give me x equals 27. If I have the fourth root of x equals 3, I would raise both sides to the fourth power, and 3 to the fourth power is 81. Again, you could check all of these. They were simple equations, so it's obvious to see that they work. All right. Same type of thing is going to happen if we have something like the cubed root of y minus 7 plus 4 equals 8. I follow the same steps as I would for a square root, where I get the radical by itself first, and then I undo the radical. So first, I subtract 4 from both sides. Now that the cube root is by itself, I cube both sides to undo the cube root. 4 cubed is 64. Then to get the y by itself, I would add 7 to both sides. That gives me y equals 71. But again, there's no property of equality that says I can cube both sides. It's only a method I use, so I have to check. If I plug in 71 for the original y, I wind up with 8 on the left side and 8 on the right side, so y equals 71 is a solution, and I circle it, or box. Number 13 is a fourth power. Again, I want to get the square root, or the fourth root in this case, by itself. So to do that, I'm going to subtract 12 from both sides. When I do that, it gives me that the fourth root is equal to negative 5. At this point, I could take both sides to the fourth power and then add 2 and divide by 7 and check my answer, but I know it's not going to work. Why is it not going to work? Because the fourth root can never be equal to a negative number. So I could stop right now and just say no solution. So the overall gist for solving radical equations is get the radical by itself, do the opposite of the index of the radical, and then make sure you check your answers at the end by either graphing or plugging into the original problem. Let us know if you have questions in Teams, and thanks for watching.